Hi everyone, this is Andy Supple with Applied Analyses for Behavioral Research. In this short video, I'm going to show you how to run a growth curve model in Mplus. Just a couple background slides first. What you're going to learn in this short video is how to run a growth curve model in Mplus using a multi-level modeling approach and a structural equation modeling approach. I'll show you and explain the difference between wide and long data, and I'll also show you how to convert a long data set to a wide data set. Another helpful thing is if you're familiar with regression or multiple regression, you've probably seen a regression formula where y, which is typically a dependent variable or an outcome, is equal to an intercept, which is basically a mean of the outcome variable when predictors like an x variable are at 0. Okay, so typically in a single level typical regression, we're not too interested in the intercept. We're typically interested in the slope, and the slope captures how much of an increase in the outcome variable you would expect given a 1 unit increase in the x variable. Okay, so generally speaking, what you get in an output here would be an intercept, the mean when the x variable or all the variables are at 0. And then beta 1 in this case is going to be the increase in y when x increases 1 unit, which is what's called a slope. And then you have a residual, which basically captures the fact that most people's estimated value for y is not exactly the same as their actual outcome score. Now, if you take this to a multi-level modeling formula with time as a predictor, which is what we're going to do when we do a growth curve, time is essentially the x variable here. So what we'll be looking at is we'll be looking at how does an outcome change when time goes up by 1 unit. That's a good way to think about it. So now we have that outcome variable. We have two subscripts, I for an individual and t for a time point. So each individual could have a particular score, but that score could also vary across the time point. So if you think about it, if someone had a score on something like anxiety, their anxiety score could be different at 4 different time points. So these estimated scores are a function of an overall sample intercept. The intercept typically is going to be the average in the outcome, usually at time 0, which is oftentimes baseline. It doesn't have to be that way, but in the examples I'll show you, that's how typically it's done, or I would say kind of the most common way it's done. Beta 1 now is capturing the effect of time on the outcome variable. So if you think about it, let's say let's say you have a study and do 4 waves of data, you could think of time 0 as being baseline, and then 1 year later would be time 2, but we would code the variable of time 0, 1, 2, 3. That'd be capturing your 1, 2, 3, and 4. So what this is doing is as time goes up 1 unit, 1 year, if that's your the distance in time between your data collection points, this slope is capturing the average rate of change over time. Okay. These are different error variances or residual terms. This is basically because it's got the 0 subscript. This is variability around the intercept. This is going to be the variability around the slope. That makes these what are called random effects. Okay, and what it means is that time, for example, or the way time unfolds in terms of leading to changes in an outcome can vary across participants or across the I people. And then the residual that captures the fact that people scores could have some error in that both, at each time point and from how an individual varies from the overall sample. There's going to be 4 key parameters in the output that we're going to be looking at. The means of the intercept and the slope that will correspond to the average score on the outcome at baseline, like I said before, typically, and the average rate of change over time. The variances of the intercept and slope basically will inform us whether or not there are between person differences in average baseline scores and changes over time. A lot of times we think about this, if you have statistically significant variance in a slope, for example, that means the way time is affecting change over time, or the way time is affecting an outcome across time could vary across participants, and then it might be interesting to see what could predict those differences in change over time. All right, enough of that. Let me now get into the Mplus. All right, so I've got a file folder here with some Mplus files. The first one I'm going to open is going to be called Model 1 MLM Approach. Okay, so if you've seen Mplus before, or if you haven't, let me get rid of that. Okay, Mplus, this is what's called a .inp or input file. In fact, let me for a second go back to the folder to show you that the files in here have an extension of .inp. Okay, so this is an input file or .imp. Those files are going to typically have a title. So these commands that are in blue are the basic commands of Mplus that are kind of general commands. Things that are in black tend to be subcommands. So title is arbitrary. You could name this anything. Note that I'm using exclamation points. And what I'm doing is I'm doing that to write comments in this syntax file or this input file. Putting an exclamation point, whatever you write after that or type after that is what's called commented out, meaning Mplus doesn't read it as a command or as valid syntax. So the title here is just growth curve using a multi-level modeling approach. Very important command. Data is telling Mplus what data file I want to be read in. So I have data file equals risky_long.csv. So I'm reading in a CSV file called risky long. I'll show you what that looks like in a second. This is telling Mplus what the data file is. It's easier if this file is in the same folder as a .imp file. If you don't have it in the same file folder, then rather than just the name of the folder, you'd also have to have the address where the data was stored to the actual folder. Mplus will not read variable names, so you need to omit those. I'll show you what I mean by that. So first I'll open up risky long. Okay, this is what risky long looks like to Mplus. So it's just a CSV file that I'm opening in Excel. So what you'll see is you'll see numbers in 4 different columns. This is what Mplus wants to see, right? If I go back to the Mplus file, I'm going to give the names to that data set. So it's going to go person ID. These are the names of the columns where the data are. Person ID, occasion, risky, at ATT12. Okay, so go back to risky long. This is going to be person ID, occasion, risky behavior, at ATT12. Okay, person ID 11111 means these first 7 rows refer to person 1. That's their ID number. So this is a long repeated measures data set. Occasion is that there is data collected at an age 12, 13, 14, 15, 16, 17, and 18 data point. So these are longitudinal repeated measures data where these are adolescents were surveyed at ages 12, 13, 14, 15, 16, 17, and 18. Technically, there's also an age variable in these data that I deleted just to simplify this, but this variable is representing the occasion or the time point at which the data are from. Risky then is a measure of risky behavior in adolescence, and these are the repeated measure scores that are going to vary across time. Okay, so one thing you'll notice is when we think about within person change or within person variability, these scores are different within person 1. The next set of scores are different in 2 different ways. They're different within person 2, but these scores are also different from person 1. That's the between person variability. And then ATT12 was mother's disapproval, their attitudes or their disapproving attitudes towards substance use when the adolescent was age 12. Okay, so those are not repeated measures, so the same score exists across the 7 different time points. Okay, so what we're going to look at is we're going to look at a data set that's got 7 points in time. Okay, it has 200 participants. So if we scroll down here, we're going to see in person ID, the numbers going up to 200. Okay, and you'll notice that the person ID is 200. That's basically the sample size, but the number of observations is going to be 200 times 7 or 1,400 observations. And those are all the different observations we have. So you'll think about it, there's 200 participants. There's 200 scores on mother's attitudes because that's time in varying, but there's 1,400 observations of risky behavior at the 7 different time points across the 200 participants. Okay, so in that Mplus file, sorry. Um, okay, so the names are, so Mplus has a variable command. This is where you tell Mplus the names of the variables in your analysis. So names equal is telling Mplus this is critically important. This has to be in the correct order of the columns. So I'm telling Mplus that that first column is the person ID variable, then it's the occasion variable, then the repeated measures risky variable, and then at 12 or maternal disapproval of substance use. The variables I want to use for a particular analysis, you do the use variables command. So this is all the variables in the data set. These are the variables I'm going to use for the analysis we're about to do. Okay, so I'm just using risky and time. This data set I don't believe has missing data, but typically you would use missing. That alerts Mplus that you have missing data in your data set. All refers to all the variables have the same missing data flag or code. Typically, I would use -99 or -999. This is multi-level modeling, so we have to tell Mplus what the cluster variable is. So the cluster is telling Mplus that there's a variable for which data are clustered within some higher order variable, and that's person ID. What that basically means is the repeated risky variable assessments are clustered or nested within person or person ID. There's going to be a within variable called time. Now notice time does not appear here. I'm going to create it down below. And then because I want to center time to be at the first time point, I'll show you that in a second. So there's one within variable, which is time. Okay, so if you think about it, time is not a between person variable in this study. Everyone is assessed at 12, 13, 14, 15, 16, 17, 18. So they don't vary in that regard. But within person, time is different from time 1, 2, 3, 4, 5, 6, 7, 8. So the variable time is a within variable factor or predictor. That's the details here about what these subcommands do. So I'm using here what's called define. The define command in Mplus is one I want to take. This is not something you always have to have in your Mplus syntax, like the variable command or the data command, for example. But define is when you want to do some centering, standardization, or any transformation of a variable. So here what I'm doing is time equals, so I'm creating a new variable, time. Now note, it's not actually in the data set. Mplus is going to temporarily create this for the analysis I'm about to run. I'm doing occasion minus 12. This is going to center time at the first time point. Okay. So occasion is going 12, 13, 14, 16, 14, 15, 16, 17, 18. Subtracting 12 turns it into time, which is going to be 0, 1, 2, 3, 4, 5, 6. So this time, or sorry, occasion, sorry, time 0 is going to be the first occasion. That's how I'm centering time so that my intercept is going to be baseline or time 0 or when the adolescents were age 12. And the analysis command, this is a command you don't always use when using Mplus, but we need it now because we need to tell Mplus that the type of analysis we're doing is 2-level, which is multi-level modeling, and random because we want to have random slopes. So we're going to create what's called a random slope eventually. But we want those slopes to be random, which means they vary across the participants in the sample. So when you do multi-level modeling in Mplus, you're always going to have a model command in Mplus. This is how you tell Mplus how variables are related to one another or associated. In multi-level modeling, you have to distinguish between your within model and your between model. Okay, so at the within level, we have risky. Whenever you see a variable name in Mplus just listed out by itself, that's referencing its variance. So this is referring to within person variance in the risky intercept variable. Then here is how you create a random slope in Mplus. So linear is not a variable in the data set. So we're creating something called linear, which is going to be a latent variable that captures change over time in risky behavior. This pipe or vertical bar is on the right-hand side is how we're defining this random coefficient on the left. So linear is a random coefficient. It's defined as risky on time. So that defines the slope factor linear. So if you think about it, risky on time is taking all those repeated measures and saying what happens to what's the association between an increase in time, a 1 unit increase in time going from 0, 1, 2, 3, 4, 5, 6. What are we generally seeing happening in the risky variable? So it's just a typical regression. But what that does is it creates this random coefficient that we can then look at the between part of the model, or at the between level, meaning each individual is going to have a linear score. Does that linear score vary across participants? So here in the between part of the model, anytime you see brackets, so brackets refer to intercepts or means. So what this is saying is at the between level, report out the average risky and the average linear. Risky is going to be the intercept. Linear is going to be the slope. And then again, if you just see variable names, that refers to variances. So also give us the variance for risky and linear, and then correlate the intercept with the slope. Okay. And the output command, this is where we can ask for things like standardization. That doesn't apply in this analysis. SAMSTAT just gives descriptive statistics. You can ask for modification indices, all kinds of other things here. We'll have some more to do here when we do this in a SEM format. So let me click run. Okay. And so here's what an output file. So Mplus in the file folder I was in has now created a file that's got it's the same name as the input file, but now the extension is .out. Mplus will give us the time and date, and then I'll repeat our syntax, tell us whether or not it terminated normally. We'll see our number of observations is 1400, as I mentioned before. There's some other details here that are not all that relevant right now. Inch class correlation, or basically how much of the variability is due to clustering. But that's not what we're interested in here. What we're mostly interested in are those four main parameters I talked about before: the mean and the intercept, the mean and the slope, the variance of that intercept, and the variance of the slope. So here we have the mean of risky. Since I centered time at time 0, okay, which is age 12, or the age 12 occasion, this basically is the mean of risky behavior when the adolescents in this sample were age 12. Okay, linear is capturing the slope, or the average rate of change over time, or a 1 unit increase in time is associated with how much of a change in risky behavior. That's a statistically significant and positive coefficient. The way you interpret this is a 1 unit increase in time is associated with a 1.116 increase in risky behavior. So what that means is, what's the effect of time on risky behavior? It's positive. As time goes on, risky behavior goes up. Okay, now we're talking about ages 12, 13, 14, 15, 16, 17, 18 in a sample of adolescents in the United States. So that makes sense that you're expecting over time risky behavior increases. So that's what that coefficient captures. Okay, then the variances are basically suggesting that there's statistically significant variability around the intercept and statistically significant variability around the linear, or around the slope. These are at the between level, which means across participants, generally speaking, there are differences in baseline scores and differences in rates of change over time. That's interesting because we might want to look at characteristics that predict both where people start in risky behavior, and also if certain participants increase more or less rapidly across adolescence. Okay, so 16.038 average at age 12 risky behavior score, 1.116. Basically, it's on average per year, there's a 1.116 increase. The assumption here is this is linear change. That doesn't have to be the case. We can test quadratics, things like that, which I'll do in subsequent videos. Right now, what I want to do is I want to show you how to now do this in structural equation modeling with latent growth curve modeling. In order to do that, we have to convert the data from long to wide. SEM uses wide format data. Let me show you what that means. Okay, so this is going to be Risky wide with variable names at the top, just so you can see what this looks like differently. This is an example of a wide data format that's more appropriate for SEM. The variables here, you'll see why in a second. It has to do with how I created this data file. But we've got our person ID variable here. And now notice instead of person ID being repeated 7 times, it's only there once. Okay, the repeated measures are wide. So now instead of a repeated measure of risky behavior across 7 time points, we have risky behavior as 7 different variables going across in a wide format. So we have risky 1, 2, 3, 4, 5, 6, 7. Now, these are the same scores we were seeing in the long data. It's just they've been turned basically sideways or wide or horizontally. So if we see person ID, now we're going to see that we only have 200 lines. Well, that'll be 201 because I have the variable names at the top if you're looking at the Excel part, but 200 participants. You'll also note that the at 12 or mother's disapproval of substance use is not repeated multiple times because this is not a repeated measures data set. So you just have that one score there. So in the long format, those risky behavior repeated measures are going down. Now they're transposed across. That's what you need to do this as an SEM model. All right, so how did I do that? So here's a file where I save long data to wide in Mplus. So the title of this is just convert data from long to wide. The file was that risky long CSV. There's a command in Mplus called data long to wide. The long variable is called risky. The wide version of that is going to be risky 1 through risky 7. Mplus is going to know that I mean by that risky 1, 2, 3, 4, 5, 6, 7. That little dash is a convenience feature to save typing. The ID variable is person ID, and the repetition variable is occasion from 12 to 18. So Mplus is going to know that what's being repeated is by occasion, which was that variable that was 12, 13, 14, 15, 16, 17, 18. Okay, so this command is going to do that conversion. The variable names of this is for the data set I'm reading in. Goes person ID, occasion, risky, and attitude 12. That's exactly like what it looked like in the last analysis we just run or that last input file. Use variables is going to be attitude 12, risky 1 through 7. Those are the variables I want to use for this conversion to wide. That's how it handled missing data. There's no analysis here or model, so those are empty. And then here I'm doing save : a save command telling Mplus I want to save a new data set. And I'm giving it a name. File is risky.dat. If I click run, I will get a data set with 200 observations. I'll get my means and variances for all the different variables. That's all I'm really interested in here. There's not that much to really scrutinize here. What I often do is, so I look down here, I've got risky y.dat. Okay, I've got the order and format of the variables. So these are the variable names that I can save out. The missing symbol is now an asterisk. I could have changed that if I wanted, but I generally don't bother with it. A lot of times what I do is I copy this and I create a new Mplus input file where I do the next step. So this file is going to be model2.latent growth curve modeling. So you'll see what I've done is created a new input file, latent growth curve modeling with wide data. The file is risky_y.dat, missing our asterisks. The names are. So a lot of times what I do, because I want to make sure I have the variable names right, in that output file, I copied and pasted the variable names here. And then what I'll do is I'll hit Control H and type F10.3, nothing in the replace with, click replace, and then delete that. And then I've got the variable names and I know they're in the correct order. That's why it's vertical like that. But that's what I would have done as a kind of shortcut to avoid lots of typing and make sure these are in the right order. So now I'm reading in risky wide. The names are mother's attitudes at age 12, then risky 1, 2, 3, 4, 5, 6, 7, and then person ID. I'm going to use risky 1 through risky 7 to do latent growth curve modeling. Now in Mplus, the way you do latent growth curve modeling, okay, is you're going to have two latent variables. I'm calling them I and S. You could just call them INT or even intercept if you wanted. it's arbitrary, but let's maybe call it INT and SLP for intercept and slope. Doesn't really matter. They're arbitrary. And then we have the pipe, which is telling Mplus that these are random coefficients. These are going to be latent variables, but they're random, meaning they can vary across participants. Okay, and this is the key of how we handle time. Okay, so in multi-level modeling, you're regressing the outcome, the repeated measures on time. That's how it's doing a 1 unit increase. Here it's a latent variable, and if you understand, I'll show you what this looks like in a figure in a second. But the way latent variables work is latent variables have directional arrows going to indicators. In this case, the indicators are the repeated measures, risky 1, 2, 3, 4, 5, 6, and 7. And what we're doing is we're setting the factor loadings to be 0, 1, 2, 3, 4, 5, and 6. And what that's doing is it's basically setting the scale of time to increase by 1 year. What Mplus needs to do is it needs to come up with a slope, sorry, an intercept value that will capture the risky score at time 0, its estimate of that, and then a slope factor. So it's got to come up with a number that represents the average rate of change as time is going across these different factor loadings that are constrained. So it kind of reverse engineers a slope score by using the observed measures on risky 1, 2, 3, 4, 5, 6, and 7. Okay, what this command does here is remember we're referencing variances when we name a variable. So doing risky 1 through risky 7 in parentheses variance would set the variances of all these variables to be equal to one another. That is going to mimic multi-level modeling because multi-level modeling assumes that. You don't have to do that in structural equation modeling. So first I'm going to comment that out so we can see that if I run it this way, I'll get freely estimated residuals at each time point, but the results will not 100% match what we got in multi-level modeling. And then I'll come back and add that back in, and we'll see that it does in that case. In output, I'm asking for sample stat, modification indices, and standardized coefficients, so I can get a little more information in latent growth curve modeling, but the most of this will be the same. This is how I'll get plots. I'll loop back around to that to show you those after we run this and go over the output. Okay, so click run. And we'll see some slight differences here. The number of observations is 200, for example. We'll get sample statistics down here, means and variances, et cetera, et cetera. So in multi-level modeling, you get a log likelihood and you get information criteria, but you don't get these other model fit statistics like you do in SEM. So we are getting a chi-square. This is indicative of not particularly good model fit because it's a statistically significant chi-square. This is the RMSEA. You'd like to see this probably below 0.08. And so this is indicative that it's not a great model fit. And then a CFI 0.931, you could argue maybe adequate. Generally speaking, I'd rather see it at 0.95. In a subsequent video, when we get into quadratic, we'll see why that there's a better way to model this change over time that is not necessarily linear, it's probably quadratic, and that's why this is not a great model fit. Okay, so what we're seeing here in the model results is first, these are latent variable models. So it's showing us these latent variables and their factor loadings. We set those to be 1 in the case of the intercept factor and 0, 1, 2, 3, 4, 5, 6. Now we didn't do anything really to get these to be 1. Mplus did that automatically for us because it got the sense of what we were doing with the IS syntax that we used above. This is going to be the covariance between the intercept and the slope. And then this is really what we're after, which is this is the average in risky behavior at age 12, and then the average rate of change over time. Now, if you remember when we did this in multi-level modeling, this was, I think, 16.038, and this was 1.116. Now the variances are 12.471 and 0.533, and then the residual variances here all kind of vary because I did not set them or force them to be equal to one another. Okay, that's about all I want to show you there. One thing I want to show you though is putting the output of the multi-level modeling approach next to the latent growth curve approach. So we get these next to each other to show you a couple differences here. So on the left, I have the latent growth curve model, and on the right, I have the multi-level model. All right, so multi-level modeling, as I mentioned, you'll get a log likelihood value, 3842. In this model, it's 3839 in the latent growth curve model. You have the AIC. They're pretty similar, but they're not exactly the same, and that's all you get in multi-level modeling. Now, multi-level modeling, you're going to get a residual variance of 8.794. The comparables here are these numbers down here. They're all estimated differently. There's not just one like there is in multi-level modeling. 16.038, slightly different. 1.116, slightly different. And then the variance for the intercept, 12.69 versus 12.47. And in the slope, slightly different. Not a big deal. But if I want those to be exactly the same, what I would do is I would comment this back in. And then what that does is, so again, this is naming the variances, but then I have a label in parentheses. A label in this instance, what it is it's an equality constraint. So what that's doing is it's telling Mplus to force all the error variances and residuals at each time point to be equal to one another. So if I do that, what I'll notice, I can look at the model fit because it should be slightly different. So actually the RMSEA got slightly better. CFI is mostly the same. What you'll notice here is these residual variances are now the same exact number. Okay, so if I pull back up the multi-level modeling numbers, if I look at the log likelihood of 3842, the log likelihood in SEM is 3842. There's there's going to be slight little differences. The AIC, they're the same number basically. Then you look at the model results, the 8.794 here, it's 8.791. So you have some slight little differences, but for the most part, these numbers are almost identical. Slope 1.16, 1.116. So when you're doing this instructional equation modeling, if you set the error variances to be equal across each time point, you'll mimic the results from multi-level modeling. That's how they're basically telling you the same thing. So average risky behavior at age 12 is 16.037. Over here it's 038, but with rounding, it's the same thing. Average rate of change over time is 1.16. Now, as I mentioned before, this is not a fantastic model fit. And one of the things to consider is whether or not there's a quadratic, meaning it's not linear change over time, but the change over time is starting to speed up or slow down. It could be either way. I'll show you in a subsequent video how to do those. The last thing, what I'll also do in a subsequent video is introduce what are called time invariant covariates, or because those slopes had statistically significant variance, it means we could explain why people are increasing more or less rapidly. Okay, so in the latent growth curve modeling model, I asked for plots. So this command plot is asking Mplus to give me data to plot out. I'm requesting a certain type of a plot. Plot 3 in the series is going to be risky 1 through risky 7. This asterisk is just telling it to just give it a number in it on a x-axis. Okay, so if I click view plots, there's a couple things I can look at here. One would be estimated individual values. This is sometimes called a spaghetti plot. So if I click view, sometimes I click random order. I've got 200 participants, so maybe I'll ask for 80 curves, and I'll just click OK. And what I see here is these are estimated growth curves for all the participants in the data set. Okay, so you have basically at at time 0 down here, that mean was somewhere in here around 16. And then what you're seeing here is that on average, you kind of squint your eyes, right? You'll see that there's an average increase of 1 point per year. Okay, and this is if it's estimated and it's linear, et cetera, et cetera. But that's essentially what this kind of looks like. You'll see variability in where people start, variability in where people finish, and possible variability in how rapidly the slope is going up. Another thing you can look at would be the the observed individual values. Okay, I can still look for 20. I can start, 80 participants in random order. Okay, I can ask for individually fitted curves. Okay, and get those. And this is if you took individual data and fitted their curve as best you could, but it has to be linear. You'd see there's some variability. There's some people in here who start lower, go up much faster. But generally speaking, you have a pattern of, on average, risky behavior going up, even though there's variability in that. So you can play around with this a little bit as well. If I go down here and do I keep clicking on the wrong thing. The observed individual values view and go to a quadratic. Okay, what you'll start to see is if we did a quadratic model instead, you'd see in general this pattern of increase, but you'll see in some cases the increase possibly speeding up. That's what I'll test in a subsequent video, but that would be the idea that as adolescents get older, the rate of change starts to speed up. That would be a positive quadratic factor. I'll come back and show you that in another video. Okay, so this video, I showed you how to do multi-level modeling to estimate a growth curve, structural equation modeling to do a latent growth curve model, how to convert data from long to wide if you want to move from a multi-level model to a latent growth curve model. Like I said in subsequent videos, what I'll do is I'll show you how to test a quadratic, how to bring in predictors of rates of change over time. Thanks for watching. Email me if you have any questions. Again, this is Andy Supple, Applied Analyses for Behavioral Research. You are welcome to reach out with questions.